In this video, we're going to cover one of the last major topics in our solutions chapter about solubility. We have talked a little bit about this topic in a couple other videos earlier in the unit, but here we're going to delve into this in much more detail. To begin our discussion today, we're going to start with an overview of some of the topics we'll be covering. First, we'll begin with a definition of what solubility is all about. Afterwards, we'll follow up with some factors that might affect solubility. Looking at this graph over here on the right, we can see already that one of those factors affecting solubility is going to be temperature. And we can see that the lines here have a curved shape to them, showing that the solubility is changing as temperature changes as well. That will be expressed in what this diagram actually is, in something known as solubility curves, and we'll talk more about how to use and interpret those. We'll then translate the idea of solubility curves into something more mathematical known as the solubility expression. There's not a lot I expect you to be able to do with the solubility expression this year, but I do like to kind of demonstrate the fact that we can express these ideas mathematically as well as graphically. Last but not least, we'll summarize all of this information into a set of things known as solubility rules that will allow you to predict in advance which chemicals are or are not likely to be soluble in water. Let's move right into our official definition then. Solubility is basically a measurement of the amount of solute that is able to dissolve in a certain amount of solvent. It is typically measured in grams of solute per 100 grams solvent. As we briefly discussed, but we'll talk about a little bit more, this solubility concept is dependent on a lot of different factors. The first of which is the pairing of the solute and solvent themselves. Certain solute-solvent combinations result in very concentrated solutions. Others result in solutions that aren't able to form at all. We can also just say that solubility is dependent on temperature, and that's exactly what this graph on the right is attempting to depict. As we increase the temperature of our solution, we can clearly see it has a very dramatic effect on the solubility of water. We're seeing this graph curve upwards, but a fairly minimal effect on the solubility of table salt. So we can imagine over a wide range of temperatures dissolving similar amounts of salt in our solution, but very different amounts of sugar. And we'll talk more about why that is in a moment. And last but not least, we can also mention the fact that solubility is affectant of states of matter. Gases, for example, have different responses to temperature in terms of solubility than solids or liquids will. Let's see if we can now try and explain some of these factors that affect solubility. The first one we'll try and talk about is the solute-solvent interaction. Like so many things we've talked about at this particular part in the year, this is dependent a lot on intermolecular forces. Those intermolecular forces exist within the solute and solvent. Those are the forces that hold all of these bonds together here, as well as the forces that hold all of these water molecules together to one another. There are also intermolecular forces between the solute and the solvent. Those would be the forces that hold these guys to one another, that allows the solvent molecules to encapsulate these solute molecules. Determining the solubility then has to do with a comparison between how strong these attractions are between solute and solvent versus how strong these attractions are between solute and solute and solvent and solvent. If these forces are stronger, that's going to translate into higher solubility. So if the forces between the solute and solvent are stronger than the forces holding the solute and the solvent together separately, then we'll expect higher solubility. We can also mention temperature and states of matter as factors that affect this. If you recall from earlier in the year, higher temperature means more kinetic energy and movement of our molecules. This generally increases the solubility of solvents. This extra kinetic energy reduces the intermolecular forces holding the solute together. As the molecules over here start shaking more and more due to the increased temperature, they start moving further apart from one another, reducing those forces, which allows the water molecules a better opportunity to reach in and pull them off to create more solution like we have over here. The faster these are moving, the easier it is to remove, and the more solution we produce. However, we can also say that higher temperature generally decreases the solubility of gases in liquids. That extra kinetic energy makes those gas particles to move faster, and when those gas particles are moving faster, they're more likely to simply escape the solution altogether and move out into the atmosphere. So here we can see temperature having two very different effects on solubility, again, both dependent on what state of matter we're dealing with. So let's turn the corner then and start talking about how we represent some of this stuff mathematically. And we'll start with something known as a solubility curve. A solubility curve is a two-dimensional plot of solute solubility versus temperature. It's typically plotted with many solutes shown on the same graph. And as we talked about, here is our temperature on the x-axis down here, and here is our solubility on the y-axis in grams of solute per 100 grams of water. Each one of these colored lines represents the solubility of the particular substance that it's labeled with. And we can see in most cases we have a general upward shift in terms of solubility. As temperature increases, the solubility of most solid salts increases. Some more very dramatically, like calcium chloride, others less so, like sodium chloride. Because there's always exceptions, we have certain substances, in this case it is cerium sulfate, that actually has a decrease in solubility as we increase temperature. Cerium sulfate is not a very common substance, but it is one of the examples that we can use to talk about substances that break the other pattern that others have. The explanation as to why cerium sulfate doesn't follow the pattern of increased solubility, increased temperatures is a little beyond the scope of our class, but just keep in mind, like so many things, there are other factors and forces at play in cerium sulfate that are absent with most compounds that cause this variation. We can then use this solubility as a tool to predict whether a solution is saturated, unsaturated, or supersaturated. Saturated solutions, and we'll use potassium nitrate as our example here, is any solution at a temperature and pressure that shows up exactly on the line. For example, if we have potassium nitrate with about 64 grams at 40 degrees Celsius, we would describe that solution as being saturated. Supersaturated then is whenever you are above the line, again keeping our example with potassium nitrate at 40 degrees Celsius. If we were able to dissolve 80 grams instead of the 40 grams, we would expect that solution to be described as a supersaturated solution. We have more dissolved than is normally capable. And then last but not least, we have unsaturated, which again can be represented by being anywhere underneath the actual curve. And my apologies for all my crossing arrows here. Again, at our same example, if we have only 30 grams dissolved at 40 degrees Celsius, we would expect that solution to be unsaturated. Going a little deeper into the mathematics, we can also express this idea of solubility with equations as opposed to just expressing it with graphs. And that is what the solubility expression is all about. Basically, how soluble a solute is in a solvent can also be represented mathematically. Solute-solvent interactions are generally referred to as a dynamic equilibrium, something a little more complex than we've talked about so far in terms of solutions. When you're dealing with a dynamic equilibrium, it's a state of balance between two continuing processes. Those two continuing processes are what we have listed down here. The first continuing process is when the solute dissolves into the solution, and the second continuing process is when those dissolved solutes come back out of solution. We typically think of dissolving as happening in one direction, but in actuality it's always happening in both. Certain things like salt, which we know dissolve very well in water, just happen to do more of the first part, dissolving into, than they do of the dissolving out. The idea of equilibrium then is when we start talking about this word balance. We reach equilibrium when the rate of both of these processes is equal, the forward reaction versus the reverse. Coming back to the diagram we used earlier on in the video, we can see again the forward reaction depicted right here. We got our solute combining with our solvent to form the product, which is now the solution of solute and solvent combined. What we haven't talked about is the fact that this process can also happen in reverse. The solute and solvent combined can separate back out into solute crystals and separate solvent. Moving over here then, as the process of dissolving proceeds, more of the solution is made, meaning we have more of the solution, and we have less of the solute available to work with. As a result of having less of the solute available, the forward version of this reaction starts to happen a little bit more slowly because there is less of the solute around to actually undergo the process. As a result, we also expect the reverse reaction to happen a little bit faster. There's much more of the solution now available, and even if it's uncommon for the solution to go back to solute because there's so much of it, the likelihood that that's going to happen is going to speed up. You can imagine then that eventually we'll reach a point where the forward reaction is slowed enough and the reverse reaction has sped up enough so that they start happening at the exact same rate, and that is when we've reached equilibrium. So putting our graphic then back into words, the balance of that equilibrium happens at different points for different solute-solvent combinations and also at different temperatures. Where this point actually occurs for your particular combination is what determines the solubility of our solution. And this point can actually be calculated by something known as a solubility expression. Now, if we go back to the beginning of the unit where we talked about our generic something going to solution reaction, where we have our salt or our ionic compound over here separating into its two individual ions, ion A and ion B, we can think of the solubility expression then as basically a measurement of the concentration, and by the way, that's what these brackets mean. So let's write a little note to ourselves over here that the brackets mean concentration. So the concentration of A at equilibrium times the concentration of B at equilibrium is going to be equal to something known as K, which is known as our equilibrium constant. And each solution combination, solute and solvent, has its own equilibrium constant that we can work with. Let's bring this back to our original goal of all this then. If we think of KSP values as being a large number, that must mean that there is a lot of chemical A and chemical B dissolved in solution, which means there must have been a lot of the forward reaction actually happening. This would mean we have a relatively high solubility. So basically we can say that the bigger value of K we get for our particular solution, the more soluble that solute must have been. So the good news is all those complicated mathematics that we might have to do using the solubility expression are actually unnecessary. We can summarize that concept of solubility and the solubility expression into a simple set of rules used to determine in advance if a solute will likely be able to be soluble in a particular solvent. These rules are typically made for ionic compounds in water. That's a very limiting kind of scenario to work with, but it's the one we work with most commonly, so it's okay. And the rules are often determined by which cations and anions are present in the solute. Different combinations of cations and anions will cause certain things to be soluble or other things to be insoluble. These rules are often summarized in tables similar to the one that you see over here on the left. This table is available for download down at the bottom of the page, and I encourage you to have a copy of this available. I believe it's also available on the back side of your periodic table in a slightly different format. The table is a little complicated at first, but it's pretty easy to use. We have a list of chemicals that are soluble on the top, so any chemicals containing these substances are likely to be soluble. And we have a list of insoluble chemicals on the bottom. Any chemicals containing these ions are likely to be insoluble. On the right side of the table, however, we have exceptions, chemicals that break the rules we're talking about here on the left. For example, we generally expect sulfates to dissolve in water, unless, say, for example, it's paired with calcium, in which case that would be an exception, and we would say calcium sulfate is insoluble, and likewise down below. Using the table is also relatively straightforward. So we can take a compound like KCl and we'll find the relevant ions on the table. Typically, it's the negative ion that determines solubility. And in this case, we see chloride as one of the halides is right here. Those are halides or chlorides are generally in the soluble category unless it's paired with silver, mercury, or lead. Potassium is neither of those, so we would say that potassium chloride is soluble. Silver chloride, on the other hand, is also a chloride, just like potassium chloride was, but silver is one of the exceptions. Therefore, despite normally being soluble, this particular chloride made with silver, we would say is insoluble. Take a minute and see if you can't repeat the process with these two chemicals down below. We got magnesium phosphate and we got sodium hydroxide. Pause the video, give it a quick try. I'll put down answers in a moment. All right, now that you've had a chance to try, let's see if we can figure these two out. We would say that phosphates in general are insoluble. They show up down here on the table. There are exceptions, namely the alkali metals, but magnesium is not one of the alkali metals. If you are curious, they're listed right up here. It's the first column on our periodic table. That would make this substance insoluble. Sodium hydroxide is also listed on the insoluble side, but again, the exceptions are the alkali metals, and sodium does happen to be one of those alkali metals, meaning we would expect sodium hydroxide to be. So that's pretty much it. At this point in time, you should be able to define what solubility is. You should be able to explain the impact that solute-solvent interactions have, as well as temperature. And you should be able to predict if a solution will be saturated, unsaturated, or supersaturated using a solubility curve. Last but not least, you should be able to describe if a solute will dissolve into a particular solvent based off of KSP values, whether the value is large or small, as well as using your solubility rules. And we'll practice all of this significantly more in class, which will eventually lead us into a lab activity later on.